Move over Netflix. Who's going to watch that anymore when you could watch a video on 5.3 properties of logs? Alright, the first formula came up in 5.1 or maybe 5.2 is the change of base formula. And it used to be really important back when calculators only had the common log base 10, or natural logs, or even before that when there were no calculators and there were log tables. The change of base formula allowed you to express logs of one base in terms of other bases. But it's still important, you should still know it, and pretty much if you want to express the log of x base a, it's the log of x over the log of a, as long as those logs have the same base. So I like to call it shortly, or more eloquent, or I like to call it log of the big number over log of the small number. Now we're going to learn a couple other properties of logs. So recall the property of exponents. So if you multiply two numbers with the same base, different exponents, you add them. If you divide two numbers with the same base, you subtract their exponents. And if you raise a power to a power, you multiply the exponents. So you could summarize that as multiplication goes to addition, division to subtraction, exponentiation, like power of a power, to multiplication. So with logs, those properties are similar. So if you were to expand a log, so on the left, if you had the log of a times b, you could express that as just the log of a plus the log of b. See, multiplication goes to addition. If you were to divide or take the log of a quotient, you can express that as the log of a minus the log of b. This is, of course, if the bases are the same. So when you just write log, it's the common log. And if you have the log of a to the m power, you can rewrite that as m times the log of a. You could also condense logs. So if you had the sum of two logs, you could write that as the log of the product of what you're taking the log of each time in each of those terms. If you're subtracting two logs and the base is the same, you can make it in terms of one log, and then you divide those two numbers. And if you have a constant times a log, you could bring that into the log as an exponent. So in class, we'll prove these properties, but for now, we're just going to practice using them. All right, and they're very similar to the exponent properties. Addition goes to, or when you multiply exponents, you add, or when you multiply numbers with the same base, you add the exponents. Division goes to subtraction, and then exponentiation goes to multiplication. So here we're going to expand out this number 13. So the first thing I notice is this number 6 here. So we're going to bring that out front, and we're going to rewrite this as 6 times the log of x cubed over y. Alright, now we can expand this out even more with that division. So we can rewrite it as 6 log of x cubed base 5 minus the log 6 times the log of y base 5. So because that 6 is in front and of that log where it's x cubed over y, then you have to put the 6 in front of both those terms. Or we could write it in front of the whole thing and just use parentheses. So we could also bring this 3 over by the x in front of the log. So you have 6 times the entire quantity, 3 times the log of x base 5 minus the log of y base 5. You might be wondering, where did this 6 go over here? Well, I just rewrote it as, I factored it out in the last step, which you could have wrote it like that, or another acceptable way of writing it is distributing it out. It's expanded either way, so it doesn't really matter, as long as you account for the fact that the 6 was in these parentheses in the beginning, thus raising x cubed and y to the 6th power. So you just have to compensate for that in your final answer by either using parentheses and putting the 6 in front, or distributing it at the end. Alright, and condensing logs. So first I'm going to get rid of these 3's, these scalar multipliers, by rewriting them as exponents. So we have the natural log of z plus the natural log of the cube root of x, or just like x to the 1/3, because dividing by 3 is like having a 1/3 out in front of the log, plus the natural log of y to the 1/3 power. Alright, so since there's only addition going on here, when we condense it in our final answer, it's all going to go to one big product. So the natural log of z times x to the 1/3 power times y to the 1/3 power. Alright, so you could write it like that. That's totally acceptable. Or if you want to write it as radical, you can also write it like that and put x and y under the same cube root. Alright, so both of those are acceptable answers. Anything with a check next to it is an acceptable final answer. Alright, and now so let's say back in this used to be more useful back in the day when there was log tables, and let's say on your table you didn't have like the log of 6, the natural log of 6, or you didn't know the natural log of 2/27, but you knew the natural log of 2 and the natural log of 3. You can express these questions, we'll call them 1, 2, and 3 over on the left, but in terms of the natural log of other numbers. So for example, the natural log of 6, you can rewrite 6 as 2 times 3. So you could break this up as the natural log of 2 plus the natural log of 3. And now you could just do 0. Well, we're just going to round here. So on a test or a quiz, I'd give you easier numbers. So let's just round these to 0.7 and 1.1 because they're irrational anyway, so we're going to be rounding. So we're going to rewrite that as 0.7 plus 1.1. So that comes out as 1.8 approximately. Alright, so the natural log of 6 is about 1.8, and you can figure that out by only knowing the natural log of 2 and the natural log of 3. So for the natural log of 2/27, we're going to rewrite that as the natural log of 2/3 cubed. And then use our expansion rules to rewrite this as the natural log of 2 minus 3 times the natural log of 3. So that becomes 0.7 minus 3 times 1.1. Then that's 0.7 minus 3.3. So that's going to simplify to negative 2.6. Alright, and then the log of 18, I would say that's best to break it up as 2 times 3 squared. And again, that might take a couple more seconds to think about if you've never seen this before, but you're just looking to express these numbers in terms of the given numbers inside the given logs. So it's going to be the natural log of 2 plus 2 times the natural log of 3. So that's going to be 0.7 plus 2 times 1.1. So that's going to be 2.2 plus 0.7, so that's 2.9. Alright, so log properties coming at you. Alright, last one. Let's just practice using the change of base formula. So evaluate the natural log of 36 base 3 using the common log. So the common log is just the log base 10. So that's when you just see like the log of x. That's really the log of x base 10. And most calculators only have the common log or the natural log. Luckily, TI Nspire allows you to change the base. So what we're going to do is express this as the common log of 36 over the log of 3. Alright, now that's something that you would, from this point on, you would need to approximate this as a decimal, you need a calculator. So let's, since I'm at a computer, let me just use the Google calculator. How can we help you? You can help me by finding a calculator. Alright, so I'm going to do the log of 36 and then divided by, how do you do that? Oh man. Alright, the log of 36 equals that divided by the log of 3, and you'll see it's about 3.2. And if you don't believe me and you have a TI Nspire, you could check that by typing into TI Nspire and changing the base. Alright, so that is all for properties of logs. We'll prove those properties in class and we'll practice them. Alright, hope you enjoyed it, and I'll see you in class.